So 49. That's the first one. It says a crate weighing 50 pounds is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. The ramp has an angle of elevation of 35 degrees. What is the amount of force being directed up the ramp? Okay, so the tricky part about this is that there's really three vectors kind of going on here. So we have our ramp vector. What's that? 35 degrees. And then, bless you, we have our crate vector. And then we also have gravity going on. So that's kind of our picture here. Is that okay? All right. So my plan here is that I have to look at the projection of G plus C onto R. So the first thing I'm going to do is to resolve G and C into component form vectors so I can add them together. So C is going to be 150, 150 cosine 48, comma 150 sine 48. And then G is obviously just 0, negative 50 because, well, just going straight down, right? So far, so good? Okay. So we're going to call this vector, I don't know, let's call it S for sum. So that's just going to be C plus G. So that's like 100.37, and then 61.47. And then my vector R, well, I'm going to, since I'm not given any information about the ramp, I'm just going to assume that it has magnitude 1. Well, other than the angle. So there's my component for the ramp. And since we didn't mention this in class, but maybe you noticed this. So for projection of vector u onto v, if the magnitude of v is equal to 1, then the magnitude of the projection of v onto u is just equal to the dot product of u and v. So that's like a little shortcut that we can use on some of these problems. You could still use like all your definitions and the formulas to do that, but this will shortcut through a little bit of it. You may have noticed that happen in the homework a couple of times, and you might have been wondering, wonder why I was getting the same number for the dot product as I did for the projection. It happens in that situation. And it has to do with the magnitude of the vector you're projecting onto is 1 already. So you scalar multiply by whatever that factor is, which is just the dot product. onto a unit vector and then take the magnitude, well, the magnitude is just the dot product then, right? Because the old magnitude is 1, so that didn't matter. It just, the result is the dot product. Anyway, so I'm going to use that shortcut now here to say the projection of S onto R, it's just going to be S dot R. So 100.37 times cosine 35 plus 6147 sine 35. To get me about 117.48 LBS. So the trick there was recognizing that you had two vectors going on, that you had a gravity vector in addition to the pull acting on the crate. You also had the force of gravity pulling down on the crate. And to just add those two together and then proceed as normally. Yeah. If you didn't make that observation in the beginning, you would have been sitting there going, how the heck am I supposed to get 117 out of this? Because this was an odd one, I think, that you could have checked. It was probably rather puzzling. But after seeing it done, it's like, oh, okay, that's an additional step in the beginning, but it's not like a big deal additional step in the beginning. It just, you know, a little bit of extra junk to take care of. Okay. What else do we got here, my peeps? Just shout them out.
We did 46 too.
46? Sure. As soon as my computer wants to feel like it wants to respond here. Sorry about that. It says, Paul is sledding down a hill with a 20-degree angle of incline. If Paul and the sled weigh a total of 180 pounds, what is the force sliding down the hill? Okay. So let's start by drawing a picture here. So we're told that the hill has an angle of incline, 20 degrees. So there's my angle of incline for the hill. If I do like alternate interior angles, I know that angle is also 20. So my standard form angle then is 340. So that's my, I guess we called it a hill there. I'll call it H then. Since we're not told anything about the length of H, I'm just going to assume that it's 1. Angle is 3, so that's just going to be cosine 340, sine 340. Notice that I drew the hill going down because we're sledding down the hill. That's why it's in the 4th quadrant as a first quadrant. And it says if Paul and the sled weigh a total of 180 pounds, so that is just being acted on by gravity going down the hill. So there's like my G vector. So there's that. So far, so good. Okay. So then we can just do our projection again. Cut through having to do like some of our steps here and just go straight to knowing the magnitude is the same as the dot product. So that's just going to be cosine 340 times 0 is just 0. 40 or sine 340 times negative 180 is that. Which comes out to be what do I want to see here? So when I type that into my pounds, maybe really what we should say about this is I guess there should be an absolute value around that. So really we have an absolute value around that dot product for a situation like this. Yup. As a crate of negligible weight is being pulled up a ramp at an angle of 38 degrees with a force of 120 degrees. The ramp has an angle of elevation of 25 degrees. What is the amount of force being directed up the ramp? So this is basically the same problem as 49. We just don't have the additional gravity vector going on, so it's a simpler version of the same problem. So here's my 25 degree ramp. Again, since I don't use its magnitude to be 1, so I can say that. And then my other vector is like there, where that's 38. I'm going to call it 8. So it says, what is that? 120 pounds of force being pulled. So my crate vector is 120 cosine 38, 120 sine 38. Notation. So I'll explain why here. We're going to give you throw a note in a moment. So let's say we have this vector in component form AB. This is equivalent to the vector AB. The notes that I gave you guys call this IB component form. When I learned this, we just call this a column vector, since it's written as a column as opposed to a row. And the reason we're going to change the notation here is because we're also going to be dealing, since we're talking about like equations of lines and stuff, we're also going to be talking about points. And the points we're going to write horizontally, and the vectors we're going to write vertically to help differentiate those two things, because it can get pretty confusing notationally if you have vectors written horizontally and then points are also written horizontally, because a component form vector and a point look very similar other than the wedge versus parenthesis. So we're just going to try to keep the vectors vertical and the points horizontal to help keep track of things, basically. Does that feel okay? So that's why this new notation is being thrown in here at this point rather than earlier. It's because it's really specific to when we start writing equations for lines and planes and stuff. Wanting to do that. Okay. So let's kind of talk through the idea here. So I'm just going to look at like a real life example of an equation for a line. So let's say y equals 1/2 x plus 1. Okay, so the equation of our line, y equals 1/2 x plus 1, looks something like this, right? Everybody's okay with that idea? If we're going to describe this line using vectors, what part of our equation for a line kind of describes the direction of the line? That's going to capture the same information as the direction of our vector. Ben? Well, so a vector has two components, right? It has a direction and it has a length, right? Now, a length for a line is going to be kind of irrelevant because the line is infinitely long. But the direction component of it is going to be important to us. So obviously the line is infinitely long, but whether we put it here or here or here or here, like where we're tilting that line at, makes a big difference to the equation for, or the equation of the line makes a big difference of how the line is tilted, right? So what part of the equation for a line helps determine like the tilt? The slope. Everybody's okay with that? Okay. So the slope for this one is is m equals 1/2, right? So basically what that's saying is that for every like 2 units you move to the right, you move 1 unit up. Everybody agree with that? So if you start at the origin, you'd go like 2 to the right and then 1 up. What does that also sound like? That sounds like the component form definition of a vector, right? Where you start at the origin and then you move like whatever the x direction is and whatever the y direction is, and that's like the head of your vector now, right? So this is going to be the equivalent of the vector 2, 1. Notice that the order of the numbers is flipped. Why are they being flipped? Go ahead. Yes, exactly right. So slope is the change in y over change in x. So the y part of slope is in the numerator and the x part of the slope is in the denominator. For a component form vector, the x part is on top and the y part is on bottom. Notice that that vector v is not a fraction, so there's no fraction bar in there. That's one of the hardest habits to drop, is like writing 2 numbers vertically and not putting a fraction bar in between them. Everybody's okay with that? Okay. So now that we have a direction for our vector, if I can find like any point P on that line, I can write a vector going this direction and a vector going that direction. That basically would cover the whole line, right? Everybody's okay with that? Because I can always scale multiply that vector as big as I need to get any points further out from that point P. So what we could say then is that our equation is basically like y equals this point plus our vector. Does this make sense, what I've written? It shouldn't. Why doesn't that make any sense? Think about the quantities that we're adding together. So let's just make this point something numeric. This could be the point 2, 2. So we'd be saying y, which is a number, is equal to the point 2, 2 plus the vector 2, 1. How the heck are we supposed to add a point to a vector? Does that make any sense to you guys? No. Right? So how are we going to fix that? Well, we'll just make the point into a vector. It's okay with that, Ben? And if we're adding two vectors together, we best be getting a vector back, right? Everybody's okay with that? Now, if we do that, though, in our case, that's just going to give us 4, 3, right? Well, that's a point on the line, but I should be able to generate any point on the line with my equation. So what are we going to do here? Well, we're just going to multiply our vector v by a scalar. What scalar should we use? Well, we need it to be variable, because if I want to be able to get any point out of there, I'm going to have to stretch v in either direction by some quantity, right? So this is like my variable. Now, typically when we write these letters, we don't use those letters. We write it with R's, and R are not V and T. Don't ask me why we settled on those letters, but that's the kind of the convention. So that's our vector equation for a line. Is everybody okay on the little journey we took to get there? I tried to start with something familiar and turn it into this without just like writing the equation down and being like, there you go. So at least kind of makes sense. All right, so let's do a specific example here about translating from a slope-intercept equation to a vector equation. Okay. So to do that, we need a point vector and a direction vector, right? Well, let's do the direction vector first. That should be easy. How do we find the direction vector? The vector v. We're going to use the slope. The slope in this case is 3, or 3 over 1. So the direction vector is going to be 1, 3. So far, so good. The point vector is not unique, right? We just need some point on the line. So what's a point that lies on this line? 0, 5. Using the y-intercept is a good one. So there we go. So we can say that r is equal to 0, 5 plus 1, 3 t. That'll do. Again, keeping in mind that your choice for the point vector is not unique, right? You could have picked 1, 8, or -1, 2, or something else that's your favorite number. I don't know. I don't know why you'd pick something other than the y-intercept if you had the choice, but sometimes people like to use weird numbers. I don't know. It's fine. Everybody okay with that? Okay. Let's go the other direction then. So let's take the vector equation of a line. R is equal to 3, -1 plus 2, 3t, and write that in slope-intercept form. So to write the equation for a line, if we go all the way back to like algebra 1 or even pre-algebra, there are two sets of information that we could use to write the equation of a line, right? I either need 2 points or I need the slope in a point. Everybody agree with that? You remember doing that like a million trillion years ago? Okay. So here, what's going to be easier for us to get, 2 points or a slope in a point? Okay, slope and a point. What's the slope then? Is 3 over 2. Good. And what's our point? Just 3, -1. Everybody go cool with that? Okay. So then if we plug this into the slope-intercept equation, like we were back in, a long time ago. Let's see, that's going to be 4.5, so -5.5 is equal to b. And just so it matches, I'm going to write it as a fraction. Oops, not 1/2, 3 over 2. Again, you could have used decimals there. I chose to use a fraction because, well, the slope was already a fraction, so I wrote the other piece as a fraction, just for consistency. Everybody okay with that? Pretty easy though, right? Not a big deal. Again, as I hopefully you feel like not lied to, very similar to what we've done in like your algebra, things we've done before, just using the language of vectors, right? So it's nothing too complicated at all going on here. The most complicated thing is going to be finding the intersection. Okay. Now, I acknowledge one way you could do this is to translate both of these back into slope-intercept equations and then like solve a system to find that intersection. I don't want to do it that way. I want to do it the vector way. But I'm acknowledging to you right now that you could do it that way. It's not incorrect. So the idea here is that we need R1 to equal R2, right? Well, R1 is basically just the column vector is a column vector. R2 should be a column vector. I have that xy is equal to the equation for R1. And we have that xy is equal to the equation for R2. And what I'm seeking to do is find that value, the values for x and y, right? So I'm going to go ahead and do my scalar multiplication and multiply that s into my vector. And similarly, I'm going to multiply that t into my vector. And then I'm going to go ahead and do my vector additions. Everybody so far so good? So this really becomes the system. X has to equal 2 plus s, and y has to equal 4 plus 3s. And this one becomes the system. X has to equal -1 plus 3t, and y has to equal 5 plus 5t. So I can rewrite this then as two systems, where I can take the x's and put them together in the same system. And I can take the y's and put them together in the same system. Oops. So when because these are both equal to x, I can say that, and since these are both equal to y, I can say that. And now I'm just going to rearrange things so that the s's and t's are on one side and the constant is on the other. And I'm going to take these two and make a system. So far, so good. I'm going to solve that system now using any method that I choose. If it's me, I'm going to use my calculator to do this and just use a matrix. I don't know if you guys have done this in your Algebra 3-4 class, but your calculator can solve any system pretty easily using a matrix. So I'm going to go and open my calculator, press second and the x and the -1 button to open the matrix menu. I'm going to go over to the Edit tab and select a matrix. And the matrix that I'm going to format, I'm going to have one column for the s variable, one column for the t, and one column for the stuff on the equal sign. And I have one row for the first equation and a second row for the second equation. So I want a 2x3 matrix. Remember, rows come first and columns come second when we do the dimension of a matrix. It'll be easy on your calculator though, because it'll line, when you do, if you did a 3x2, you'd be like, well, that doesn't look right, because the things are in the wrong spots. And then the numbers that we're going to put into our matrix are just the coefficients we see. So the coefficient on S is 1, the coefficient on T is -3, and then it equals -3. So I have 1, -3, -3 for my first row. And my second row, the S coefficient is -3, the T coefficient is -5, and then it equals 1. So I have 3, -5, and 1 in my second row. Everybody okay with how I set that up? Basically exactly the way it looks in my equation. I just dropped all the operators and the variables, right? I just left the coefficients. Okay? Once I've set that up, I'm going to exit out. I'm going to go back to the matrix menu. This time I'm going to go to the Math tab. And down at the bottom, you're going to see the command RREF. So if you scrolled all the way down to the bottom, you'll see this command RREF. Make sure you pick the one with 2 R's, because there's also REF. That's not the one you want. You want 2 R's. Okay. And we'll do that RREF command on the matrix A. That spits out this as an answer. And somehow, Mr. Kulik is going to claim that that answer tells you what the values for S and T are. So we did RREF of the matrix 1, -3, -3, 3, -5, 1. And that gives us the matrix 1, 0, 4.5, 0, 1, 2.5. Well, we can read this equation, or this matrix, as a system of, it says 1s plus 0t is equal to 4.5. Well, doesn't that just mean that s is 5? And I can read the second equation as 0s plus 1t is equal to 2.5. Hey, doesn't that just mean that 2.5? Everybody so far so good? Okay. So now that I know the values for S and T, I can pick one and go back and find my value for X and Y. So for example, I know that X is equal to 2 plus S, and y is equal to 4 plus 3s. So that's going to be 6.5 for x, and let's see, that's 12, 13.17.5 for y. Here. And now you say to yourself, like, yo, Mr. Kulik, that was like a lot of stuff. It really felt like it would have been a lot easier to just convert those into slope-intercept equations and solve the system directly. And I understand what you're saying, and I agree. In a two-dimensional situation, that is the case. We're not going to be working in this chapter in just two-dimensional situations. We're also going to be working in three-dimensional situations, and if you continue to take like math classes for a long time, you'll see situations where you're talking about like any dimensional vector, in which case like this method becomes considerably preferable, because as you get to higher dimension, the conversion between the linear form and the vector form becomes much more difficult, and this becomes actually quite preferable, although it doesn't feel like it right now. Okay with that? So again, practice this method, because we are going to do three-dimensional pieces. I think in the next chapter we start talking about 3D stuff, which is a bit more challenging. And this method is going to be basically the exact same method in 3 dimensions, but it's going to make life, I think, considerably easier if you're comfortable with this method in 3 dimensions than if you're trying to convert things back into linear equations and trying to solve those systems. I think this will be quite preferable. So this is where I'm going to stop for today. I think we've probably done enough here. What I would like to do here with the remaining 30 minutes or so of class, I have our homework quiz for this chapter. Not in your notebook, apparently. I'll go grab it from the other one. So let me copy that and paste it back where it needs to be. So we're going to do that. And then sync this notebook. So for the remainder of class, you guys can work on this homework quiz. When you're finished, you can just upload that to the Dropbox and PowerSchool. I'm making the Dropbox right now, so if you're going to look for the Dropbox immediately, it'll take me a second to create the assignment or whatever, but this should be completed before you leave today. So it should be relatively straightforward. There's nothing in here that's requiring anything much more than putting some numbers into some equations on things that we've done in class already. So it should be okay. If you run into problems, let me know. But the idea here, you're going to do this in OneNote, so you'll copy this page into your own OneNote section, do it in OneNote, export that file as a PDF, and then load it into the Dropbox on PowerSchool like we did for the practices earlier this year. If you have technology problems or anything, let me know. I'll be happy to help. Is everybody clear on that stuff? And then there's homework problems, obviously, due from this section. I think there's a lot of them. That's already posted, and PowerSchool is due for this coming Sunday's homework check. But I think it's a lot. Although these particular problems, I think some of them are quite simple to do, so I don't think it'll be that bad, but I think there was a lot of numbers. I don't remember off the top of my head, but I wrote it down on PowerSchool, so you could do it there, or you could see it there. If you need to move the plug-in, you're welcome to do that. I can see you're getting your charger out already. There's extension cords in all over the place, so if you need one. Oh, yes, of course, Sophia. What was I doing? That's what I was going to do. You can sit there, it's fine. Yes, sir. Yes, sir. Please do. More than fine to do that. Certainly can leave them as radicals. No big deal there. In fact, honestly, I find that preferable. But if you convert them to decimals, that's okay too. It's not a big deal. I mean, I think it's more work because you got to type it, another line in your calculator or whatever, but radical is okay. So that's that. My people's working from home. I'm going to unscreen share because we're, kind of done doing stuff. You're just working on this homework quiz. And again, if you want to go offline to do that, you're welcome to do that and just submit. You don't have to stay on the Zoom call. We're kind of done doing things. So if there's a more comfortable place you want to move to do your work, totally okay doing that too. Or you can stick around in case you run into something. You're like, I'm going to just hang around because I probably end up wanting to ask a question about something. That's totally okay. You can do whatever you want. It's no big deal to me. Just thought I would give you the heads up, just trying to be flexible.